today and tomorrow's training session, and hopefully we'll be able to jump right into the presentations. And let me go ahead and thank all of the presenters in advance for their time and their presentations. Doing such a remote event is not easy and can be frustrating, and I thank them for their patience and time. So really quickly, just introduce the 4 stacks that are part of the NIH Cloud Interoperability Platforms Group, NCPI, also called the Interoperability Group. We have the Anvil, funded by NHGRI, Biodata Catalyst, funded by NHLBI, the Cancer Research Data Commons, funded by NCI, and the Gabriella Miller Kids First Data Resource Center, funded by the Common Fund. I'd like to do some really quick introductions of the 4 stacks. Is Allison Heath on yet? Hey, Allison, do you mind doing a quick spiel about Kids First?
Sure. Hi, Mo.
Hi, thank you.
So Kids First, we have this kind of fact sheet put together where you can get some more details about us, and I think I'll be doing some demos tomorrow as well. So the Kids First program was started a couple of years ago out of congressional funding to really fund the pediatric structural birth defects and cancer. So when a lot of people first hear that, they often ask, why are you studying structural birth defects and cancer together? But it turns out there's really a unified scientific umbrella around developmental biology in the landscape there. Especially if you think about pediatric cancers, there's not, kids aren't sunbathing, they aren't smoking. There tends to be different kinds of predispositions and things happening developmentally. Structural birth defects are often happen by things not growing, right? So, heart valves not closing, or the skull not forming fully. So oftentimes the underpinning genetic etiology of a lot of these diseases have a lot of similarities, and a lot of diseases that haven't been studied as robustly as some of the common diseases. So the efforts around Kids First was really to do whole genome sequencing, mostly family-based. So it's usually the parents and the kids, whole genome. In the cancer cohorts, we also are doing RNA-seq as well as deep whole exome sequencing on the tumors themselves. And so from the very get-go, we had this mandate of really integrating across a lot of disease types, and started out thinking about how do we best empower that landscape. So we brought in a lot of the data. We have created kind of a different little pieces there where we have a portal that people can initially land on, and then Cavatica is our cloud-based workspace that we can push that towards. We've also been looking at other different visualizations. We're very interested in not rebuilding things when there's things that already exist, but how do we integrate and have the data kind of flowing to different services, different platforms, different visualizations. I think especially traditionally in pediatrics, a lot of times the data has been siloed, but I think there's also, not only do we want to look across pediatric disease sets, but there's a lot of interest in cross-integrating that across ages. It's not like when people turn 18, suddenly their biology changes. I think there's a lot of interesting things across that different landscape and different visualizations. There's a lot of data out there. There's a lot of modalities out there. No one of us is really going to create all the best, greatest visualizations or platforms or workflows. So very interested in kind of the experience of folks kind of getting in there and working with it, because I think the flip side of what I just said is often from a kind of user researcher standpoint, you don't want to go to 100 different platforms to get the job done. So where do we find that kind of sweet spot of having kind of the core platforms, but also allowing people to go between them as they get their work done with their different data and scientific goals. So, and I'll point out that our GitHub is there. Everything's open source. We're trying to get things better documented and out there, and happy to talk about any of the technical parts with anyone who's interested later on as well.
Awesome. Thank you, Allison, and sorry for not telling you in advance that I would ask you to do that spiel.
No worries. I'm glad I was actually showed up on time. So.
Is there anybody from Biodata Catalyst that can give a quick spiel on the line? can start calling on folks. Brian O'Connor, Garrett, Andrew Rula, would you guys like to say a few words?
I'm happy to. Oh, sorry. Go ahead, Brian.
Sure, I can give a bit of a background here. So this is work from NHLBI. This is involving quite a few institutes. Garrett definitely helped me out here because I haven't had caffeine yet, so I may not be making any sense. But on Biodata Catalyst, I think what's very interesting about this platform is it's not just one platform, but it's many different components that are working together. So we have multiple sort of workspace environments, Gen 3, Terra, 7 bridges. And yeah, so this is a good diagram of the various components there. We have Picture for searching metadata, clinical and phenotypic metadata. We have multiple APIs available. We have a repository for workflows and tools and apps in the future. So in its own way, Biodata Catalyst is very much like an ecosystem of components. And so that's why it's always been, on the forefront of how systems talk to each other and interoperate with each other. So I would say that's from an architectural, and I'm going to be biased more towards thinking about it from an architectural and stack perspective versus a data perspective. But from a stack perspective, it's really focused on how we interoperate within within the consortium, but also external. And this is probably a good point, Garrett, if you do want to jump in here and talk a little bit about the data, in the system, since I kind of gave a bit of a background on the components that make up Biodata Catalyst.
Sure. So I'm actually, even though I pretend to be many times not the data expert for Biodata Catalyst, but we've worked to ingest a large number of top med data sets that are all varying in terms of the data that's provided, but still focus on heart, lung, and blood disorders primarily. So we have both genomic and phenotypic data available. And to Brian's point, I think I'm also always biased towards the architecture, and I would just reiterate that I think that the Biodata Catalyst project is a great micro example of the work that we want to do here in terms of interoperability. I'll talk about it a little later in the Gen 3 section, but we have a lot of these interoperability conversations around PFB as a potential handoff mechanism, around implementing things like RAS, et cetera. And these are all the kinds of questions that have been relevant to the Biodata Catalyst project from the beginning because of its focus on utilizing so many different organizations' work. And I'll probably leave it there.
Thank you, Brian, Garrett. Cawthor, are you on the line? Can you say a few words about CRDC for us?
Actually, Bill Longabaugh here, and I'll be handling the slides.
Thanks, Bill. I'm skipping ahead to the architectural diagram.
I've skimmed over all the slides. I'll just ask you to go ahead when the time comes. Okay, thanks. So anyway, CRDC basically started in around 2014. NCI set up 3 cloud pilots, including 7 bridges, the Broad Institute, and the ISB. So we operated as cloud pilots for about 3 years. And again, the vision was to get cancer data up into the cloud to make it, first of all, practical for various, the usual reasons for putting stuff in the cloud, right? So worked that through, and then around 2017, we transitioned from being pilot projects to being cloud resources. So originally, there were the 3 different pilots, and they would each be hosting the data in the cloud, but the architecture, the long-term architecture came into being 3 years ago, where separate data nodes exist, hosting the data, and the cloud resources work on top of that. And there's and since then, other nodes have come up. So originally we started off with the GDC. That's now fronted by the Data Commons framework, also at the University of Chicago. Similarly, the Proteomics Data Commons has been brought up, as the Imaging Data Commons is currently under development for an MVP this summer, and then the Integrated Canine Data Commons. So and that list is growing. So next slide, please. There we go. Thank you. So the GDC continues to be putting out releases pretty much monthly these days, adding new data sets all the time. Proteomics data node is also putting out, bringing up new data sets, and the imaging commons is working first of all on the TCIA data set. So there's also, in addition to the data sets available at the nodes, ISB-CGC hosts 300 data sets available in BigQuery tables. You can bring your own data and work on it there. And as I say, the data continues to grow. So the tools themselves, the resources as well as some of the nodes also provide tools. So Seven Bridges has their publicly available tools and workflows in CWL. And they also do notebooks and RStudio. Broad has many workflows as well as notebooks, BigQuery pipelines, and so forth. You can see the list there basically. GDC, for example, has their data visual analysis. You can look at it and look at the data there. And PDC also offers some tools as well. Next slide. So right from the start, the issue is how to get to controlled access data in the cloud, and all three compute resources support this. So again, using ERA Commons IDs, originally everybody worked directly with ERA Commons work directly with NCI or NIH to get people authenticated. Now it's all done through Fence as part of the NCI, the Data Commons Framework at UChicago. So we all use Fence. And actually, as we speak right now, there's the issue of bringing up the Researcher Authorization Service, the RAS service, which will be cross NIH, and trying to work out how to work against that service now. So basically, we use dbGaP access privileges to figure out who's authorized to do what, and that's all handled by Fence. In addition, DCF at UChicago provides indexing, so we have the IndexD system. So bottom line is all of the files that are being hosted in DCF, and for that matter in any other node, are run through IndexD. So we have globally unique identifiers, which can then be accessed, for example, through Fence to get signed URLs, or also using Google native authentication. Everybody's got their own data model, given the fact we all started off separately, so that everybody's got their own data model, but the Cancer Data Harmonization Center is working to come up with a combined model to coalesce on as time goes on here. And GA4GH is also something we're looking at, both with respect to DERS as well as the new authorization stuff. Next slide, please. And so here we'd have the final architecture diagram. So very tiny, who can see what, but bottom line is over there on the left, all the various data nodes. Actually, the green guys are the ones that are recently coming up. The blue ones have been around for a while. The resources are there at the bottom, sort of the blue arrow, yeah, in the middle there. Dark blue arrow, that's the one, thanks. And the resources are there. And over here on the right, we have an architecture diagram. So this reflects sort of the early on, the commons used to be, the cloud resources used to be the whole ball game, but as it moves over through time, we have the various data nodes that sort of popped up along the bottom of this, and the resource data commons sit on top of it. The new block right there in the middle, the cancer data aggregator, has yet to exist. It's currently under bid, but the idea being is you want to be able to find this different modalities of data through a unified process, unified system. And so the cancer data aggregator is being brought in to provide a single query point to find data across all the nodes. And I do believe that is the last slide. So thank you.
Yes, thank you, Bill.
Yep.
In the interest of time, I will speed through the Anvil slides. Anvil was started late 2018, funded by NHGRI. Anvil is led out of Broad and Johns Hopkins. There are many satellite sites, including University of Chicago, UCSC, Vanderbilt, OHSU, Penn State, Washington State, and St. Louis. The data that we have is mainly population-based human data sets, so security is extremely important. The data sets that we currently have on Anvil are the CCDG, CMG, 1000 genomes. The latest version of GTEx will be onboarding eMERGE and some other clinical related data sets soon. Skipping ahead to our architectural diagram, from a high level, we use Gen 3 to index our data. Terra is our compute engine. DocStore is our workflow repository. The tools that I'd like to highlight are RStudio with bioconductor support and Galaxy that will be integrated towards the end of this year. This is all in a FISMA moderate environment running on Google Cloud Platform, where we pass on the billing to our user so the user has control over their own scaling. Thank you again to the folks who introduced their platforms and had no idea that they were supposed to speak. Moving on, Brian O'Connor, would you like to share your screen and tell us a little bit about the ongoing efforts for making our platforms interoperable?
Sure, I'd love to do that. Let me go ahead and share my screen here.